Hi everyone. So in this short video, I want to show a really neat result, which is an elegant constructive proof that the degree of R as a Q vector space is infinite. That is, if we consider the real numbers as a vector space over the rationals, it cannot be finite dimensional. Now the usual proofs have to do with cardinality arguments, and namely we have that R is uncountable, whereas Q is countable, that is, can be put in bijection with the natural numbers. And this already shows that R cannot be finite dimensional over Q. But we want to take this a step further and find an explicit set of real numbers that are linearly independent over the rationals. Right? So let's recall what it means to be linearly independent over a vector space if the set is actually infinite rather than finite. So let V be a vector space over the field K, and S as a subset of V is linearly independent if the following is true. If we have the set of all, let's say, C sub I, Vi equals 0 implies that all Ci are equal to 0, where these are taken over all, let's say, finite subsets of S. We write all the conditions down here, right? So we check this on finite subsets. And now here we want to find a collection of real numbers, right? So that is going to be, the reals are going to be V here, and this is considered over the field Q. So we want to find a set S of real numbers that are Q linearly independent. So I claim, and this is somewhat surprising, we can take S to be the logarithms of all prime numbers, log P sub I, where Pi ranges over primes. And in the rest of this video, we want to show, in fact, that S is Q linearly independent. Well, how do we show this? That the set, let's say log 2, log 3, log 5, so on, is linearly independent? Well, we want to check it using the criterion above, which is you look at it over finite subsets, and that we can't have any non-trivial linear combination of finite subsets there, over finite subsets, I should say. So let A, B, and S consist of the finitely many elements, let's say log P1 all the way through log Pn for some unspecified n, and all that matters is that if we choose this arbitrarily, then we want to show that C sub I log P sub I, where I ranges from, let's say, 1 to n, equals 0, implies that all of the Ci are 0, where these coefficients come from the ground field, which in this case is the rationals, where C sub I is in Q. Well, first we can say since each c sub I is rational, we can express it in lowest terms, let's say. Let's say each ci equals ai over bi, where ai and bi are coprime. Right? And in that case, we have the linear combination a1 over b1 times log p1 plus all the way through an over bn times log pn. And this is equal to 0. So we can multiply through by, let's say at best, I think the tightest bound here is the least common multiple of the b sub I over here. But if we take this at a coarse level, we can just multiply through by the product of all these b sub i's. So no need to be super fancy here. And this doesn't change anything. So this is looking at a trivial linear combination over these a sub I times log pi. So we're going to multiply through by b1 times bn. So this is the product of these bi. Where now we have a1 log p1 plus etc. an log pn equals 0, where each of these a sub I are integers. Okay, well now we can transform this equation over here into, using very simple log rules, the following. So we just have each of these by using the simple exponentiation rules. This means that this combination is equal to 0. And once again, we use simple log rules to conclude. We turn the sum of these logarithms into the logarithm of their product. This is equal to 0. Okay, now what can we do to both sides? Well, we can raise these by taking e as the base, and each of these is the exponent. Then e to the log p1a1 times pn a to the n equals e to the 0, which means that the log of this product over here, we're now, since these obviously cancel, we have p1a1 pn times an is equal to 1. Okay, but the following fact now comes in handy, and this is the, I think, most beautiful part of this argument here. These p sub I are primes, so we have this decomposition as 1 as a product of prime powers. Now, because of the fundamental theorem of arithmetic, by unique prime factorization, there can only be one way to express 1 as a product of prime powers, and that is if we take all of these exponents to be equal to 0. And this is for all I. But this implies in turn that each c sub I, which equals of course ai over bi, is equal to 0 as well for all I. And that is exactly what we wanted to show, looking back on it, right? Because we wanted to take these combinations here and then eventually show that if we have some linear combination of these log p sub i's, then each of the coefficients have to be 0, which is exactly what we've just done. Hence, log p sub I as I ranges, let's say these demarcate the prime numbers, forms an infinite let's say Q linearly independent subset of R. All right, thanks for watching.